In this section, we'll look at conditional probability density functions, and we'll look primarily at equations, and then we'll come back next week and look at more examples of how to actually utilize conditional PDFs. But for the meantime, let's just go ahead and jump right in. So the first thing that you may recall is that we had a probability mass function, some p of x, some random variable x, and we said that the probability mass function for a random variable x is just equal to the probability that the random variable x is equal to the specific value, the argument that we're passing into this probability mass function. And likewise, we had for probability density functions, or PDFs, this equation where we said that the area of probability, the probability density function multiplied by its width, that delta, was basically the probability that the random variable x was between x and x plus delta. Now, we can also say from probability mass functions that we had this equation where we said that the probability mass function of a random variable x when conditioned on a was just equal to the probability that our random variable x was equal to, again, this argument little x, when it was conditioned on a. And the same thing applies when we make it to the probability density functions. We say that the probability density function of some random variable x when conditioned on a, again, we're doing this multiplied by delta, so we get an area, is approximately equal to the probability that x is between, the random variable x is between x and x plus delta when it's conditioned on a. Again, this is a lot of equations. Like I said, we're going to come back and look at some examples here pretty quickly and then some more in-depth examples next week. But we can extend this and say that the probability that x, a random variable, is an element of some event b, we could say was the sum over all values of that random variable that are an element of b multiplied by the probability mass function of the random variable. So this is only looking at those probability outcomes, those random variable outcomes that are an element of the event or of the set B, and then summing all of the probability masses at those outcomes. Now, likewise, we can say for a probability density function that the probability that a random variable x is an element of a event B or of a set B is the integral over all of the b's. And again, that's the integral of the probability density function. So we're just saying, hey, over all of these events, integrate to sum them all and get their areas. And that is the probability that the random variable is a part of this event B. Now, extending that to conditions, we can say that the probability that our random variable is an element of B when conditioned on A, we just said was the sum over all of the x's that are a part of B. Again, same thing as unconditionals. But then it's the probability of x when it's conditioned on A, specifically the probability mass function of the random variable x when it's conditioned on A. And likewise, we can say for a probability density function that that probability is the integral over all of B of the probability density function when it's conditioned on A. So we're using all of these terms and we're saying, hey, when they're conditioned on A, and we're going to come back to that here in just a brief second. But the last one we'll look at is saying that for all probability mass functions, we said that the sum over all of the values of a random variable x of the probability masses when conditioned on A must still equal 1. Again, it's kind of like we're replacing our sample space, and our sample space always has to equal 1. And the same applies with conditional probability density functions, where we can say that the integral over all of the probability density functions of x when conditioned on A must still equal 1. So just because we're conditioning, we still have to have our total probability density over everything be equal to 1. Now, with all that kind of tucked away, let's go ahead and look at a graphical example just to maybe help cement these concepts a little bit. And like I said, we'll look at a lot more examples next week. But first, let's go ahead and look at this graph right here. So we have two different graphs, one on top, one on bottom. And just so you can remember, we said that the probability that a random variable x is between some value x and x plus delta when conditioned on the fact that the random variable x is an element of this event or set A was roughly equal to the probability density function of x when x is conditioned on being an element of A multiplied by delta. So with that, we can look at a very specific event A. So let's go ahead and say that our event A is these red lines here. And so as you'll notice, they're the same top and bottom, but on the top graph, our x to x plus delta region is not part of that event, and on the bottom it is. So with that in mind, let's go ahead and try to figure out what this looks like. So if we say that for the top graph, we can ultimately pretty visually say, hey, x to x plus delta, there's none of this that is part of the event A. And so it's pretty intuitive to say that this should be 0, right? That there should not be any probability of that occurring because we've limited our scope to being this region here, this area. So let's find an equation that works, and we'll take our top equation and kind of extend it a little bit. And let's say that we have the probability that the random variable x again is between x and x plus delta, where x is an element of A. Again, the same thing. And we can never forget that for conditional PDFs, we have to scale everything. And so we're going to divide that by the probability of the event A. So from there, let's look now at our bottom example. Here we've said in this case that we can just intuitively look and say this should be 0. But in this case, we have this region right here that is between x and x plus delta, and it's conditioned on A. It's part of the event A. And so what that ends up looking like at the end of the day is when we say, hey, let's go ahead and scale this, right? So if we were to scale everything over the probability of A, we'd end up with a graph that looks something like this. So this is now, because of the event A, we have to increase the values of our conditional probability density function. We have to raise it such that we have all of this area now, this space, being equal to 1. Again, that's our goal. We're dividing out everything that's not there. We're getting rid of it and scaling the rest of it so we still have a 1. So now our new area, x to x plus delta, is this region right here within the random variable x. So this blue region is the conditional probability density, whereas if we look outside of that, this purple is not part of our region. So we're looking at really the ratio now of the blue area to the purple area, or the blue area really to the blue plus the purple area to get the correct percentages. So we can kind of summarize this and turn this into an equation, just these two fundamental principles, and say that the probability density function of a random variable x when x is an element of the event A is just equal to 0 if x is not an element of A. And so that's this top graph here where we said, well, if they don't have overlap, then they don't give us anything. And then the other side of it is that we say, hey, it's just the probability density function of x again. But we're going to divide by the probability of the event A. We're going to divide by this total probability here in order to scale, again, that total probability density function. And this is only valid if our x is an element of A. And it's important to remember that for any type of conditional PDF or any type of conditioning, that we have to assume that the probability of the event A occurring to begin with must be greater than 0. We have to assume that the event A actually has a probability of occurring that is greater than 0. Otherwise, we end up in this divide by 0 situation down in this equation here. So with that, that's where we're going to go ahead and leave it for this week. Like I said, next week we're going to jump right back in with a series of examples to help cement this.